today's lecture is about transmission lines, and we will start with the mechanical design of transmission lines. So first off, transmission lines generally, and when we're talking about transmission lines for purposes of today's lecture, we will include those in transmission and distribution systems. Generally, transmission lines are most commonly in overhead configuration, so you can have overhead or underground cables. In the case of overhead, they generally look like this. This is the pole mounting of transmission lines. Usually, you will have either a 3-wire or a 4-wire system. Most commonly 3-wire systems, as we had said last time, in transmission and distribution, all the way down to 11 kV. And usually the 4-wire systems would be the direct lines to consumers. So whatever consumers will be receiving at their supply will be usually in 4 wires. So in the cases of this particular diagram, you have a pole mounted electrical distribution system or transmission lines that are pole mounted. Now, in the case of overhead lines, you will generally have bare wires, and that is one of the main advantages of overhead wires, that in most cases, the wires will be insulated by the air itself. They'll be insulated from each other by the property of air not to conduct electricity. And that is sufficient for you to transmit your power in a system that is overhead. In the case of underground cables, these will be dug under the ground, they will be buried, and you will have to have insulation and protection, mechanical protection, to prevent any damage or water ingress into the underground cables. Generally, for all types of overhead cables, we have 2 types of materials, either copper or we use aluminium. In the case of copper, copper is the better conductor, but it is also more expensive. Aluminium in turn is lightweight and more durable, because copper cables tend to have deterioration and they are more susceptible to corrosion than with aluminium. So let's look further at the pole mountings of overhead cables. So this is your standard pole. When you walk outside, you will see generally this kind of pole, slightly different configurations from place to place, but the components of the pole themselves usually are the same. We can start from up here. This that you're seeing, the insulator, prevents the cable itself from directly coming into electrical contact with the pole, and that will lead to a short circuit and a fault. So you have to completely isolate it electrically from the pole. The pole itself can be concrete, can be wooden, and can be metallic. Down here, you will find on each of them, you will have a ground wire. These are there as a protection in case you do have a fault, such as, for example, if you have a lightning strike, you would need a path to be created that would safely discharge that lightning strike to the ground. In the case of this pole, you will notice we have a transformer that is pole mounted. In this pole, as an example, you have 2 levels of voltage. On the upper level, we are seeing we have a primary feeder, which is most probably at 11 kilovolts, 11,000 volts. Then the primary feeder makes a path through to the transformer and out to the cables that are there. This is low voltage, probably 415 volts. This is your high voltage. So in between the two, you must have a physical separation. So you'll notice that the higher voltage is at a physically higher height, a greater height, and the low voltage is at a lower height. And this is one thing that you will note with electrical poles. Sometimes, in fact, you will find poles, since the infrastructure already exists, other services will make use of the same poles that are constructed by distribution companies such as Kenya Power. So you'll find people like fiber internet cables or telephone wires, those ones will also be mounted on the same cables. But in order to do that, they will usually be mounted at an even lower level so that you have your lower construction. So it goes, the highest voltages are at the top and you go downwards in order of decreasing voltage level. So the connection between the high voltage and the transformer passes through a number of protective and insulating devices. We've noticed at the top you have the feeders themselves. Those are the wires that are mounted through the insulator and they are clamped onto the pole itself. In addition to that, you now have your connector. Here they have indicated a hotline clamp or a solderness connector. You do not weld the connectors there. They are mechanically fixed using bolts or other forms of joining devices. And you have a connector which we sometimes call a dropper. Below here you have your fused cutout. The purpose of the fused cutout is in case of any maintenance or fault work, you can safely isolate the high voltage system or the high voltage circuit from the rest of the gear that is mounted on the pole. So in this case, the transformer and the low voltage wires. The fused cutout, you can see it is a bar that connects at the top with the dropper from the high voltage line. So that in case you want to disconnect the circuit, you would disconnect it from there. Generally, you will see the Kenya Power teams, if they need to do any work on the transformer or on the lines that are coming out of the transformer, they would disconnect the high voltage lines using the fused cutout. This is a side view, but generally there would be 3 fused cutouts for each of the 3 phases. Of course, you have a series of insulators that are there. These also prevent the connection of the fused cutout to the pole. They separate it from the pole itself. So from there, you will note that now you have your dropper that has come through and it is connected to the transformer, the primary winding of the transformer. A pole-mounted transformer usually would be a 3-phase transformer, but in certain areas, like in rural areas, you can find single-phase transformers. But generally in densely populated areas, such as urban areas, you will have 3-phase transformers that are mounted on the poles, and you will always find them mounted above the secondaries. Now, one thing that is not indicated in this diagram is usually below the transformer, you would have a set of fuses for the secondary low voltage lines. Before the low voltage exits or leaves the transformer, you could actually disconnect them. And those are in the form of physical ceramic fuses that are mounted 1 per phase below the transformer itself. Those ones are very easy to see. I would encourage you, next time you actually see a transformer along the road, just stop, have a look at it, see if you can identify all the components of your transformer. Underground cables are usually in areas where it is not prudent or it is not possible to have overhead cables. So in places where, like, for example, it's a residential area, let's say, and residents would like to maintain kind of the scenery or the beauty of the area. You don't want to have your poles spoiling the environment or spoiling the look of the area. Another example is where it is not practical to do overhead cables. For example, an area with a lot of buildings like the CBD of a city, you will find most of the cables will be underground. You can find your substations within the CBD, but you will not see overhead cables leaving from there, simply because they are tall high-rise buildings and it would not be safe to have them there. Other examples, you can have undersea cables or underwater cables, cables that need to cross a body of water, a large body of water. It would not be practical to put poles. You need to put underground cables. So whenever you will encounter overhead lines, you will generally notice that they are mounted on poles, but they are not tightly stretched. The cable that is in between your poles will generally have kind of a sag looking like that. And what you will find is that whenever you have those lines in between, the reason why we have that sag is to allow for things like heat, the expansion and contraction of the lines themselves. Remember, this is copper and aluminium over long distances, hundreds of meters and perhaps even kilometers. And so you need to allow for that. Also, you need to allow for the cable itself to rest in a position where the tension is not exceeding its own mechanical strength. So when you're looking at the design of the wires, here we have assumed that all of them are there. You would have your 3 wires, but for simplicity of the diagram, let's indicate only one of them. So here we have a couple of descriptions. So the distance between the 2 ends or the 2 mounting points, the distance between those 2 ends is called the span. The distance at which it is hanging from its highest point, which is there, is called the sag. So those are the 2 main distances that we will look at. So let's look at this particular cable. So if you have, this is your lowest point, point O, and this is your connecting points. Let's call this point B, that is point A. Your span will be the distance from A to B, right? And your span, let's call it L, so that this distance to the center is L over 2. This is also L over 2. If you take a point, and your sag here, sag is denoted by S. Now, let's take a point, say there, let's call that point P. Now, at point P, you have a distance from O that is denoted by X, and a height from the lowest point, which is denoted by Y. Now, what are the forces that are acting on the wire itself at point P? You have 2 main forces. You have gravity, or the weight, which acts downwards, and you have tension, which at point O acts in that direction. Now, the tension will be the same at every point along the span, along the cable itself. So that tension will be the same one that will still be acting at that point. So generally, the forces that are acting at point P are the weight and the tension. And because your wire or your cable is at rest, these forces are equal to each other. They balance each other out. So in order for us to calculate the various forces and the various properties of the wire mechanically, you will take the moment of the forces around point P. So for this section here, let's take it as point P. If we assume that the weight of the cable is equally distributed along the cable itself, so the moments due to weight will be W times X. If W is the weight per unit length, X would be the length from here to here. And that the resulting point of action of that weight would be at the center of your piece of segment of cable. So the action of that gravity would be acting at that point. And it would be a point in between the 2, which is a distance of X over 2. Remember, X was from the center point to the point where P is, and Y is from the point of the center to the height that is there. So the total moments due to weight will be Wx times X over 2. Yeah, the length times the force. Now the moments due to tension will be similarly acting in that way. T is acting from the point O to the point P. So the moment of that force will be given by T times Y, because it is acting along that whole distance that we have there. Now, what we then do is we equate those moments. Because it is at rest in a balanced state, Ty is equal to Wx squared, which is these two together, over 2. Those are the moments of the forces around point P. And we can simplify it further by saying y equals Wx squared over 2t. So this particular formula is the equation that describes the shape of this particular sag or the tension itself. At any point, anywhere along this line, whether it is point A, whether it is point O, whatever it is, this characteristic will hold true. The distance y, the height from the bottom or the height from the lowest point, will be equal to the weight per unit length times the horizontal distance from the lowest point over 2 times the tension encountered within the cable. Remember that the force of tension is the same all along the cable. So we'll now do an example. A transmission line conductor is strung across a river crossing and it's supported by 2 towers at heights of 70 meters above water level. So that is one tower. Let's represent the other tower by this much. And it is strung across that. And you have your water here. The horizontal distance between the 2 towers is 300 meters. And you have your height, which is unknown. Find the clearance from the point midway. So this is your point midway, halfway there, and you're looking for the clearance, which is here. And we know it is 70 meters high. However, suspension length of the string is 2 meters. So 2 meters means from the top to the point where the string is suspended is 2 meters. And we know the total height of the whole tower is 70 meters. You can also calculate the sag in order to find the clearance. So 70 meters is equal to clearance plus sag plus the suspension length, which is 2 meters, which we already know. And this distance from here to here is half of the span, which is 300 meters. So span, in this case, the height y is equal to wx squared over 2t. So x is that and sag is y, right? So x is known, 150, because it is half of 300. T is known, it is 1500 kgs. And w, we need to know the weight per unit meter, the density times the cross-sectional area, which is given by density is 8.9 grams per centimeter. But because it is grams per centimeter, we change it to kilograms. So times 10 to the power 3 per meter. And then the cross-sectional area is 0.9, but we convert it to meters. So square centimeters converted to square meters is 10 to the power minus 4, right? And that gives us, we bring in the calculator again, 8.9 times 0.9 times 10 to the power minus 4. That gives us 0.801 kilograms per meter. That is W. So now we have all that we need in order to calculate that sag. So y is equal to 0.801 times x squared, which is 150 squared over 2 times 1500. So it is 0.801 times 150 squared divided by 2 times 1500, which is about 6 meters. So we can now get the clearance. So clearance equals the total height 70 minus 6 meters of sag minus 2 meters of suspension, which gives us 62 meters, right? So have a look at further work. Further work will then now look at towers with heights that are different from each other. So 30 meters and 90 meters.